Okay, we are live after a long time. Today I'm in Pune and I'll be doing live from here. Let's study a bit because I'm not feeling good. I think I will feel better if I study. So let's go for it. I'm sitting on a bed, not on a chair because I'm just having a stomachache. But let's get back to the study for now. Also, I've not been speaking in English for a while, so let's see if I speak right or not. Okay, Chapter 5, Introduction to Recursion. And often enough, our faith beforehand in a certain result is the only thing that makes a result come true. Yeah, true. Most algorithmic strategies used to solve programming problems have counterparts outside the domain of computing. When you perform a task repeatedly, you're using iteration. When you make a decision, you exercise conditional control because these operations are familiar. Most people learn to use the control statements for, while, and if with relatively little trouble. Before you can solve many sophisticated programming tasks, however, you will have to learn to use a powerful problem solving strategy that has few direct counterparts in the real world. That strategy, called recursion, is defined as any solution technique in which large problems are solved by reducing them into smaller problems of the same form. The italicized phrase is crucial to the definition, which otherwise describes the same strategy of stepwise refinement. Both strategies involve decomposition. What makes recursion special is that the subproblems in a recursive solution have the same form as the original problem. If you are like most beginning programmers, the idea of breaking a problem down into repetition or conditional testing. Wait a minute. Recursion is not a concept that comes in day to day life. Because it is unfamiliar, learning how to use recursion can be difficult. To do so, you must develop the intuition necessary to make recursion seem as natural as all the other control structures. For most students of programming, reaching that level of understanding that takes considerable time and practice. Even so, learning to use recursion is definitely worth the effort. As a problem solving tool, recursion is so powerful that it at seemed at times seems most magical. In addition, using recursion often makes it possible to write complex programs in simple and profoundly elegant ways. A simple example of recursion to gain a better sense of what recursion is. Let's imagine you have been appointed as the funding coordinator for a large charitable organization that is long on volunteers and short on cash. Your job is to raise $1 million in contributions so that the organization can meet its expenses. If you know someone who is willing to write a check for the entire $1 million, your job is easy. On the other hand, you may not be lucky enough to have friends who are generous millionaires. In that case, you must raise that $1 million in smaller amounts. If the average contribution to your organization is $100, you might choose a different tack. Call 10,000 friends and ask each of them for $100. But then again, you probably don't have 10,000 friends, so what can you do? As is often the case when you're faced with a task that exceeds your own capacity, the answer lies in delegating part of the work to others. Your organization has a reasonable supply of volunteers. If you could find 10 dedicated supporters to in different parts of the country and appoint them as regional coordinators, each of those 10 people could then take responsibility for raising $100,000. Raising $100,000 is simpler than raising $1 million, but it hardly qualifies as easy. What should your legal coordinators do? If they adopt the same strategy, they will then turn delegate parts of the job. If they each recruit 10 fundraising volunteers, those people will only have to raise $10,000. The delegation process can continue until the volunteer are able to raise the money on their own. Because the average contribution is $100, the volunteer fundraisers can probably raise $100 from a single donor, which eliminates the need for further delegation. If you express this fundraising strategy in pseudocode, it has the following structure: void collect contributions int n. If n is less than equals to 100, collect the money from a single donor, else find 10 volunteers, get each volunteer to collect n by $10, combine the money raised by the volunteers. The most important thing to notice about this pseudocode translation is that the line get each volunteer to collect n divided by $10 is simply the original problem reduced at a smaller scale. The basic character of the task, raise n dollars, remains exactly the same. The only difference is that n has a smaller value. Moreover, because the problem is the same, you can solve it by calling the original function. Thus, the preceding line of pseudocode would eventually be replaced with the following line. True. It's important to note that the collect contributions function end up calling itself if the contribution level is greater than $100. In the context of programming, having a function call itself is the defining characteristic of recursion. The structure of the collect contributions procedure is typical of recursive functions. In general, the body of a recursive function has the following form: if test for simple case, compute a simple solution without using recursion. Else, break the problem down into subproblems of the same form, solve each of the subproblems by calling this function recursively, and reassemble the solutions to the subproblems into a solution for the whole. This structure provides a template for writing recursive functions and is therefore called the recursive paradigm. You can apply this technique to programming problems as long as they meet the following conditions. You must be able to identify simple cases for which the answer is easily determined. You must be able to identify a recursive decomposition that allows you to break any complex instance of the problem into simpler problems of the same form. The collect contributions example illustrates the power of recursion. As in any recursive technique, the original problem is solved by breaking it down into smaller subproblems that differ from the original only in their scale. Here, the original problem is to raise $1 million. At the first level of decomposition, each subproblem is to raise $100,000. These problems are then subdivided in turn to create smaller problems until the problems are simple enough to be solved immediately without recourse to further subdivision. Because the solution depends on dividing hard problems into simple ones, recursive solutions are often called divide and conquer strategies. The factorial function. Although the collect contributions example illustrates the concept of recursion, It gives little insight into how recursion is used in practice, mostly because the steps that make up the solution, such as finding 10 volunteers and collecting money, are not easily represented in a C++ program. To get a practical sense of the nature of recursion, you need to consider problems that fit more easily into the programming domain. For most people, the best way to understand recursion is to start with simple mathematical functions in which the recursive structure follows directly from the statement of the problem and therefore easy to see. Of course, the most common is the factorial function, traditionally denoted in math as n factorial, which is defined as the product of the integers between 1 and n. In C++, the equivalent problem is to write an implementation of a function with the prototype int fact parenthesis int n that takes an integer n and returns its factorial. As you probably discovered in an earlier programming course, it is easy to implement a fact function using a for loop, illustrated by following implementation. The implementation uses a for loop for cycles through each of the integers between 1 to n. In the recursive implementation, this loop does not exist. The same effect is generated instead by the cascading recursive calls. Implementations that use looping, typically by using for and the while statements, are said to be iterative. Iterative and recursive strategies are often seen as opposites because they can be used to solve the same problem in rather different ways. These strategies, however, are not mutually exclusive. Recursive functions sometimes employ iteration internally, and you will see some examples of this technique in Chapter 6. The recursive formulation of fact, the iterative implementation of fact, however, does not take advantage of an important mathematical property of factorials. Each factorial is related to the factorial of the next smaller integer in the following way. N factorial is n multiplied n minus 1 factorial. Thus, 4 factorial is 4 multiplied 3 factorial, 3 factorial is 3 multiplied 2 factorial, and so on. To make sure that this process stops at some point, mathematicians define 0 factorial to be 1. Thus, the conventional mathematical definition of the factorial function looks like this. N factorial is 1 if it is 0. If n is 0. Otherwise, it is n multiplied n minus 1 factorial. This definition is recursive because it defines the factorial of n in terms of the factorial of n minus 1. The new problem, finding the factorial of n minus 1, has the same form as the original form, which is fundamentally the characteristics of recursion. You can then use the same process to define n minus 1 factorial in terms of n minus 2 factorial. Moreover, you can carry this process forward step by step until the solution is expressed in terms of 0 factorial, which is equals to 1 by definition. From your perspective as a programmer, the practical impact of the mathematical definition is that it provides a template for a recursive implementation. In C++, you can implement a function fact that computes the factorial of its arguments as follows. If n is 0, the result of the fact is 1. If not, the implementation computes the result by calling fact n minus 1, then multiplying the result by n. This implementation follows directly from the mathematical definition of the factorial function and has precisely the same recursive structure. Tracing the recursive process, if you work from the mathematical definition, writing the recursive implementation of fact is straightforward. On the other hand, even though the definition is easy to write, the brevity of the solution may seem suspicious. When you are learning about recursion for the first time, the recursive implementation of fact seems to leave something out. Even though it clearly reflects the mathematical definition to recursive formulation makes it hard to identify where the actual computational steps occur. When you call fact, for example, you want the computer to give you the answer. In the recursive implementation, all you see is the formula that transforms one call to the fact into the another one. Because the steps in that calculation are not explicit, it seems somewhat magical when the computer gets the right answer. If you follow through the logic the computer uses to evaluate any function call, however, you discover that no magic is involved. When the computer evaluates a call to the recursive fact function, it goes through the same process it uses to evaluate any other function call. To visualize the process that you have executed the statement as part of the function main, when main calls fact, the computer creates a new stack frame and copies the argument value into the formal parameter n. The frame for fact temporarily supersedes the frame for main as shown in the following diagram. It hurts. I'll see you in a while.